Welcome to Nuclear Energy, from Physics to Power. My name is Dr. Tom Haynes from the University of East Anglia, and today we're going to talk through some of the basic science of how to cure cancer, go to space and save the world. How do we get energy out of the nucleus? As you can see on this figure here, from the left in comes a neutron and it hits a uranium-235 atom. The uranium-235 absorbs the neutron and becomes a metastable uranium-236. A few fractions of a second later, or fractions of a femtosecond later, the uranium-236 metastable nuclei splits apart, releasing fission products, which have an awful lot of kinetic energy, which is also known as heat, and 2 or 3 other neutrons. And managing how those neutrons are used in a nuclear reactor is more or less the entire point of a nuclear reactor. Here you can see a typical pressurized water reactor. The yellow and orange circuit is the primary circuit, and the water in that circuit remains as water. It doesn't boil. And the reason it doesn't boil is because of the pressurizer, which heats it up and increases the pressure so that the water remains as a liquid even at incredibly high temperatures of about 325 degrees. In the blue circuit you can see in the middle is the secondary circuit, and you can see the steam generator. And the primary circuit boils water in the secondary circuit, and then that steam goes through the turbine, turns the generator, and produces the electricity. One of the key parameters to understand in a nuclear reactor is a criticality factor, K. That is the ratio of the number of neutrons in the current generation to the number of neutrons in the previous generation. For most of the time for a nuclear reactor, K is equal to 1. So the number of neutrons in this generation is equal to the same as the number of neutrons in the previous generation. And the reactor power is constant, or it is 0. If K is very much more than 1, we have the case of a nuclear bomb. But if K is only a little bit more than 1, it's a nuclear reactor which goes supercritical, but it's increasing its power. If K is less than 1, that's a nuclear reactor which is decreasing its power. So if 1 neutron is needed to cause the next fission event, what happens to the other 1 or 2 neutrons being produced out of each fission event? Well, most of the time, the neutrons do absolutely nothing. They go straight through the reactor, out of the walls and into space. And in fact, space is full of neutrons. One of the more interesting things that can happen in a nuclear reactor is that material can absorb a neutron. In this case, you can see a target nuclei, which has absorbed a neutron. That then becomes a compound nucleus, which has an additional neutron on it, and relatively quickly it releases a gamma ray. That gamma ray can go off and generate some of the heat in a nuclear reactor, and about 4% of the heat in a nuclear reactor is actually by these gamma emissions. And then that leaves behind a new nuclei which has an extra neutron compared to its starting point. One classic example of this is nickel-58, which absorbs a neutron to become nickel-59. The nickel-59 has a half-life of about 76,500 years and is actually really important for nuclear waste. For the earlier generations of nuclear reactors, they use normal steel, which has quite a lot of nickel in it. However, nickel-58 in that steel captured a neutron to become nickel-59, and so that steel is now radioactive with a half-life of 76,500 years. Newer reactors are being designed which contain steels with almost no nickel at all, meaning that those reactors can be disposed of and the sites returned to as brownfield sites before many of the reactors which have been shut down decades before. So what happens to a neutron if it doesn't get absorbed by matter? Well, one of the things that can happen is elastic scattering, and these are very much like billiard ball collisions. So the neutron comes in, hits the target nucleus, and is then recoiled. And these interactions conserve energy. The opposite of elastic scattering is inelastic scattering. In an elastic scattering, a neutron is absorbed by a nucleus to become a compound nucleus. Sometime later, the neutron is emitted from the nucleus, leaving the nucleus in an excited state, which then subsequently decays away by gamma emission. That gamma emission has taken some of the energy from the neutron, and so the neutron has reduced its kinetic energy. The neutron is said to have been transformed from being a fast neutron to a slower neutron. Moderators are an important part of a nuclear reactor because they slow down the neutron and make it more likely that the neutron can cause a fission event. What this graph shows is the fission cross-section for uranium-235. And we can see that as the incident neutron energy decreases, the cross-section increases. And so we see that the neutrons go from being fast neutrons when they're created to thermal neutrons when they become in thermal equilibrium with the surrounding reactor. Of particular interest to nuclear physicists is the resonance region in the middle. That resonance region can actually give you quite a lot of information about the internal structure of the nucleus. What makes a good moderator? Ideally, we want an efficient moderator, and that is one in which the nuclear reactor is as small as possible. We ideally want the moderator to not be absorbed, so that helps our neutron efficiency and ultimately means that we can use less uranium-235. We would also like our moderators to be cheap and easy to maintain. One of the first moderators to be used in nuclear reactors, and still used in Canadian CANDU reactors, is heavy water. It's an incredibly efficient moderator, and so the nuclear reactors can be very small. One of the reasons that heavy water is so efficient is because it absorbs far, far fewer neutrons. That's because we have deuterium in the water rather than standard hydrogen. So the low absorption leads to better neutron efficiency. The downside of heavy water is that it's expensive and hard to obtain. One of the older moderators to be used is graphite. Graphite is a relatively inefficient moderator, and therefore the nuclear reactors have to be much, much bigger. It also has a relatively high neutron absorption cross-section, meaning that some of the neutrons are lost from the reactor. However, on the good side, it's cheap and easy to maintain, and the graphite itself can be part of the structural body of the reactor. However, for some reactors that becomes problematic as the graphite is eroded away over many years. Normal water or light water can be used as a moderator. Normally distilled water is used, and the moderation is incredibly efficient. The reason for that is that the hydrogen nuclei have more or less the same mass as the nucleus. That means that the nuclear reactors can be very small. The downside, though, is unlike heavy water, the neutron absorption cross-section for hydrogen is much, much higher, and therefore some of the neutrons are absorbed by the moderator. The benefits, though, are that normal water is cheap and easy to obtain. But how do we get our energy out of the fuel once we've generated the heat? Well, to do that, we need a coolant. What makes a good coolant? Well, ideally we want something which is not activated, that is to say it doesn't absorb neutrons. We want something with a high specific heat capacity. We want something with a high density, a high thermal conductivity, something which is not corrosive, something which is cheap and abundant, and no phase changes. That is to say we want it to be and to remain a liquid if it is a liquid and not to start boiling. The first coolant to be used was air. However, air is moderately activated. It has a very low specific heat capacity. It has a low density, a low thermal conductivity. It's actually fairly corrosive due to all the oxygen and all the water in there. However, air is cheap and abundant and is already a gas. Following an accident in 1957 at Windscale, carbon dioxide began to be used as our primary coolant in the United Kingdom. The advantages of CO2 is that it's low activation, it's not corrosive, and just like air, doesn't undergo any phase change. However, the disbenefits are that it still has a low specific heat capacity, it still has a low thermal conductivity, and that actually, compared to air, it's not as cheap and not as abundant. Heavy water has also been used from the dawn of the nuclear age. The advantage of heavy water compared to light water or normal water is that heavy water containing deuterium is not activated as much as standard water. It has the same high specific heat capacity, the same high density, and the same high thermal conductivity, and provided you keep it under pressure, there is no phase change. However, just like water, it is corrosive, and unlike water, it is expensive and hard to obtain. Pressurised water reactors make up the vast majority of the world's nuclear reactor fleet. They are efficient and they are relatively small, which makes them a little bit cheaper to make. However, the temperature is limited to 325 degrees Celsius because if you go above that temperature, the water becomes very corrosive to the zirconium alloys used for the reactor internals. If we want to make our reactor go hotter, and we will need to do that if we want to use nuclear power to decarbonise industry, we need to have a step change in how the nuclear reactors are designed. High temperature gas-cooled reactors. As the name suggests, high temperature gas-cooled reactors have a gaseous coolant, in this case helium. That means that the corrosion issues associated with pressurised water reactors are reduced and the reactor operates at a much higher temperature. This will hopefully enable us to decarbonise process heat. The molten salt reactor is another approach. In the molten salt reactor, the fuel is actually dissolved in the coolant, and that is passed round and round the core, which contains the moderator and the control rods. Not only is the molten salt reactor able to run at higher temperature, it also burns its own waste, meaning that the nuclear waste is dangerous, well, more dangerous than the ore it was mined from, for 300 years for a molten salt reactor compared to the 300,000 years for a conventional nuclear reactor. We'll also talk briefly about nuclear fusion, or in particular what nuclear fission can tell us about nuclear fusion. We're also, next session, going to move on to talk about some of the consequences of nuclear reactors, what can go wrong and what can be done to prevent them from going wrong. So, whilst nuclear reactors can save the world by reducing carbon dioxide emissions and reducing climate change, there are other fantastic reasons to be engaged in nuclear technology. Whatever happens, we are going to need nuclear technology, not just for energy generation. Radioisotopes are key for radiotherapy. Traditionally, cobalt-60 has been used for radiotherapy, and the gamma rays from the cobalt-60 are focused down on the cancer and are used to help destroy the cancer. These days, however, the X-rays, which are the same energy as the gamma rays, can be used by a linear accelerator at the hospital, reducing the risk of contamination to the environment. So where does the cobalt-60 come from? Put simply, it can be produced from one of the spare neutrons in a nuclear reactor. So here we can see on the left our traditional fission event with a neutron coming in, causing fission in uranium-235. The first neutron will go off to cause the next fission event, whereas a second neutron can actually be used to impact a cobalt-59, and that increases its mass to become cobalt-60, and that cobalt-60 is radioactive. The other way in which nuclear science can be used in healthcare is to help detect tumours and help image the brain. Technetium-99 is used for over 80% of nuclear medicine procedures. The advantage of technetium-99 is that it's chemically versatile, which means it's very easy to get into you. The gamma rays emitted are also low energy. That means that it's not going to do too much damage to you on the way out. The 6-hour half-life means that most of the emissions are going to happen when you're being examined, and also the emissions are very specific energy, which makes those emissions easy to detect, and the total activity inserted into the patient can be lower. Technetium-99 is a decay product of molybdenum-99, which is itself formed as a fission product of uranium-235. Now, the half-life of molybdenum-99 is only 66 hours. That means that if you want to use technetium-99 in a hospital, you need to be relatively close to the nuclear reactor. Electronic components can't get too cold. If they do, they stop working. And so when space probes are sent to the other side of the solar system, they need to be kept warm. And a radioactive heating unit is the way in which it can be done. So having a core of alpha-emitting plutonium-238 means that a radioactive heating unit can produce 1 watt of heat. That is enough to keep your electronic components warm enough so that they work. The plutonium-238, however, is made in nuclear reactors and is actually one of the byproducts of the fission process itself. So that's an overview of how we get from physics to power using nuclear energy. Or as I like to look at it, how to cure cancer, go to space and save the world. In the next session, we're going to have a look at some of the novel nuclear reactor designs and see what the advantages and disadvantages of these are compared to the existing reactor technologies.